So we are on the second part of the eye. We did not even start doing this on Monday, so you can see that my slides are different. That I actually had difficulty creating a voiceover for those old slides, and I had to change things around a bit. But so we were talking about the introduction to vision, and what we've done so far are 1 and 2 in this title slide. So we talked about the properties of light. We did the introduction to the eye, and really in the overall introduction to vision, also we're still in the eye, are the properties of the photoreceptors are very important for how we see the world. We're back on the retina, so the back kind of lining of the eye. On the back of the eye, we have what makes up the retina are these photoreceptors, along with really the pigment epithelium and the neurons that the photoreceptors communicate with. But these photoreceptors include rods and cones, at least at this back level of the retina. And the rods and cones are what are allowing us to see. And there are differences between the rods and the cones. They differ in their physical appearance. They differ in their distribution along the retina, or where they lie exactly on the retina. They differ in their wiring to the brain, which we're going to talk about as influencing both acuity and sensitivity to dim light. That a little bit overlaps with functional significance. But then after wiring, we're going to talk about the clinical issues that we can see with each. And between the wiring and the clinical issues, you can really see, I think, the functional significance, but we'll still explicitly go through the functional significance of the rods as in comparison to the cones. So this is a scanning electron micrograph. I think I've got those in the right order of the rods and the cones, with the rods being those larger rod-like looking things, and the cones kind of looking like cones. I think it takes a little bit more imagination, but their names are describing their physical appearance, and they do appear different from each other. They differ in their distribution across the retina or along the retina. So if you look at the x-axis, what we're looking at is angle or degree, where 0 degrees is basically showing the fovea. If you go back to that previous talk, and you can see it in the eye next to it, the fovea is kind of close to the center of the retina, and it is why we are moving our eyes around the world. We want to, the whole optics of the eye, the whole goal is to focus that information on the fovea so that we get that crisp, clear, acute vision. And you can see in the slide, so the cones, we're seeing them in red, in the red line, and the rods in the blue line. The cones, we have most of our cones right there in the fovea, and then they have this quick drop off as we move out to even 1 or 2 or 3 degrees of visual angle, which is just, if you think about the eye being 180 degrees around, that we have so much visual angle. So when we're close to the fovea, we still have some cones, but as we're moving out, you can see that we get very few cones along that entire periphery. When we're in the fovea, if we look at the rods, there are absolutely no rods in the fovea. What we're going to talk about the foveal vision giving us, because of those tightly packed cones, is that acute vision. And the rods are really doing something different. And so if you think about, if you're looking at this slide and kind of thinking about attending to what's in your peripheral vision, you'll notice that it's a little bit blurrier. It still has color because we do have some cones out there. But so we have this large amount of rods as we're into the fovea, but not in the fovea, but we're not too far out. And we kind of see this drop off a little tiny bit as we get more and more out in the periphery, where if you think about how it's 150, we don't really see that well. If you put your hand up way over to your right, you can see movement pretty well, but unless you can't see how many fingers you're holding up or any such thing if you're far enough over. What you'll also notice on this figure is that big brown bar in the middle of the graph, that is representing the blind spot, okay, where we have absolutely no photoreceptors. And you can see it on the picture to the left, that we have to take this information to the brain. The neurons are going to send their axons to the brain along that optic nerve. So the optic nerve has to leave the eye. We also have blood vessels coming into the eye, which in the picture to the left is kind of shown in the yellow. So at that spot, that's not too far from the fovea, we have a blind spot because there are no rods and cones doing the job of transduction so that we can see the world. Okay, I usually do this in class, and I have my quick and dirty finding your blind spot, and it's kind of fun, and there's almost always at least a few people in there who've never seen their blind spot. I want you to seriously consider doing this. You don't have to actually print up the page. I was doing this with my screen the other day, and it works. So if you have this on full screen, you can close your left eye, and with the X kind of lined up with your right eye, and it's easier probably to move your face back and forth, but you might, if you have a laptop or something where you can move it back and forth. Not sure it would really work on a small phone, but if you made the picture as big as the phone, so you closed up in the picture, it might work. I think it would. Where you go closer and further and closer and further, and eventually the mouse disappears. And I ask here what happens with the stripes. Usually we do this with a white piece of paper so you don't see that background, but I'm going to give you the answer because no one's here to answer me. The stripes, they fill in. Okay, so we don't get just this white blob where we don't see anything, but our brain fills in the information that makes the most sense for it to be there. Okay, we're going to do another one because some people have a really hard time not moving their right eye. Other people have a really hard time not moving their left eye and just looking over to what that is in the periphery. So I'm going to do it one more time with the other eye. Here again, you don't really have to print up the page because it works with the screen, and you might hear me actually moving closer and farther as so now you're going to close your right eye and look at the fixation cross with your left eye. And you can either move your head or face closer and farther, or you can move the laptop or whatever you're using closer and farther, and eventually that little circle that's in the center, it disappears, and I can ask you what happens to those lines, those concentric lines. And hopefully you notice, hopefully you're taking the time to do this and maybe pausing, you notice that they fill in, and so instead of this empty circle, it looks like the lines touch each other and go across the circle. Again, our brain filling in with what makes the most sense given the environment. So usually in class we stay on that page for a second, and I have people tell me why is this happening, what's going on, and someone from the class is realizing this is my blind spot. This is the place on each eye. If we close the other eye, we can, and some small thing falls within that blind spot, we can see, basically, kind of, if you will, our blind spot, where that lies, where we don't have any rods or cones that are taking in visual information. What normally happens, because we have two eyes and both eyes are open, is the other eye is filling in. But also, if you notice, when you close one eye, you don't have this sense of a blind spot because, as I said, as we saw with the lines and the stripes, the brain fills in the information from the surrounding information, so that it all gets kind of glued together and it makes sense. And it's just one of these examples of how our perception is not precisely representing what's out in the world. It's giving us a perception that makes sense to us. And again, so that blind spot is because the optic nerve is leaving, and we have blood vessels entering the eye at that spot. The rods and the cones also differ in their wiring to the brain. So I'm going to be talking about that for a little bit, but you can see this kind of wiring, and I do compare it to some electrical circuits as that same kind of wiring. But so we have, in each eye, we have 126 million photoreceptors. They are doing the job of transduction. They are changing the electromagnetic energy into electrochemical energy that the brain can understand. And they are going to communicate to the brain through these 1 million retinal ganglion cells. You can see in the picture, he's basically showing 4 photoreceptors converging. So we see this convergence to 2 retinal ganglion cells. But remember, this is 126 million photoreceptors to 1 million retinal ganglion cells. And in between there, we have these bipolar cells, which are part of this circuitry that allows for some of the convergence that's going to occur. We're also going to look at those horizontal cells and amacrine cells very briefly. But right now I'm putting convergence that it's happening at the level of the bipolar cells, really, and between the bipolar cells and the photoreceptors, but also between the bipolar cells and the retinal ganglion cells, so that we can communicate this information to the brain. So I'm going to start with the wiring of the foveal cones, the cones that are in the fovea. They have basically a linear circuit, a 1-to-1 circuit, so 1 cone to 1 retinal ganglion cell. And what this gives us is high acuity. And I feel like there's no sense of me explaining why until I get to showing you the electrical circuit, because otherwise I'm talking about really something really abstract. In just a couple slides, I'm going to show an electrical circuit that shows why this 1-to-1 circuitry is going to give us high acuity or a really good perception of detail, good detailed vision. There's convergence in the peripheral retina because we have those 1 million retinal ganglion cells, and we have all these 126 million or so rods or cones. We have about 150,000 cones in the fovea, but they're going to have a 1-to-1 circuit. So we're going to have a lot of convergence in the peripheral retina, and it's more so for the rods than the cones. We have about 120 million rods per eye and about 6 million cones per eye. So if we look at the convergence onto those retinal ganglion cells, we have more convergence for the rods at about 120 to 1, 120 rods to 1 retinal ganglion cell than to cones that we have about 6 to 1, so 6 million cones to 1 retinal ganglion cell. And what this convergence gives us is a spatial summation, because these rods and cones are lying in space along that retina and taking in information about visual space, and we're summing that or converging that, and it gives us an increased sensitivity to dimmer lights, okay, to lower light levels, but it gives us a decreased resolution, so we do not get that same acuity or good detail vision that we have in the fovea. And again, I'm going to show this with an electrical circuit and hope that that makes sense once you put it together with the picture. Okay, I was really planning and excited to be doing this in the Monday class because I thought I could draw on this PowerPoint, but here we go. This electrical circuit on the left is really showing why there's increased sensitivity for those rods that are doing the convergence and why we get decreased resolution. So I'm going to play some kind of hypothetical games with these numbers as well as with the lights that are out in the world. So we're going to start with the left, and we're going to say that those red balls are the bipolar cells, okay? And we're going to start hypothetically that they need 10 units, okay? They need 10 units of activation in order to fire. So we have these 5 lights that are out in the world that are hitting those 5 rods in the left-hand picture. And so let's just say each of those rods are sending on, with this light level, they're sending on 2 units of activation. It's a little bit made up of how this happens, but the electrical circuitry works the way that the eyes work. So it's the way I'm going to do it. So if they're each sending on 2 units of activation and they're all sending excitatory information to that bipolar cell, what we see is, I'm going to move from the left to the right, 2 plus 2 plus 2 plus 2 plus 2, that equals 10. And that bipolar cell is going to respond and say, yes, there's light out in the world. Okay, I'm going to look at the right-hand part of the figure. And again, I'm going to pretend for now that these bipolar cells need 10 units of activation to fire at all. So if they don't get 10 units of activation, they just don't fire. And these are cones, and so they have the linear circuit that we were talking about that's happening in the foveal vision. And so if there are those 5 lights out in the world, and I'm looking right at them, and you can think of this as looking at stars or something, and they're hitting those foveal cones. They're very dim light. Each of those cones is sending on 2 units of activation to each of those bipolar cells. None of those bipolar cells are getting up to the 10 units of activation that are required for them to say, yes, there's light out in the world. So those dim lights that are giving us 2 units of activation, we just don't see them at all. There's no response. Okay, so I'm losing that sensitivity to dim light. I'm going to use this same diagram to kind of explain how the cones give us detailed vision and acuity. But now I'm going to pretend, okay, I'm just going to pretend that this is hypothetical. I'm going to start on the right-hand side this time, where we were with the foveal cones, and I'm going to pretend that those bipolar cells, let's just say, they need 2 units of activation to say, yes, there's light, to have some response and tell us that there's something out in the world. Okay. When we have 5 lights out in the world hitting those 5 cones, and so we have all 5 of those bipolar cells are saying, yes, there's a light out there. Okay, let's look at, well, let me stay there. Let's say that so take the second and the fourth. Okay, so there's 1, 2, 3, 4, 5 working from left to right. And again, we're looking at the cones in the right-hand side of the picture. Let's just say the second one and the fourth one, those 2 lights are turned off. Okay, so now what we see, because we have each of those bipolar cells responding to a light that's out in the world, is the first bipolar cell is responding, yes, there's light. The second one is saying, no, there's not a light here. The third one's saying, yes, there's light. The fourth one's saying, no. The fifth one's saying, yes, there's light. And so we can see that there's just 3 lights, and they're separated by some point of darkness. Okay, now let's move to the left-hand side. And again, we're going to pretend, we're going to change our hypothetical units, that bipolar cell, that little red ball, that is representing my bipolar cell, we're going to have it respond even if there's 2 units of light. It's the same, or two units of activation, just like we did on the right-hand side. So if that's responding to 2 units of activation, and we have those 5 lights on out in the world, right? We're seeing 1, 2, 3, 4, 5, or 4, or 2, 4, 6, 8, 10 units of activation. And so what's going to happen at that bipolar cell is it's going to respond faster, but it's still just 1 bipolar cell responding faster. And what we're going to do is the same thing we did on the other side of turning off the second and the fourth light. Okay, if we do that on the left-hand side, we turn off the second and the fourth light. The first rod is giving 2 units. The second rod is saying, no, there's nothing. It gives nothing. The third rod is saying, yes, there's something out there. It sends 2 units. The fourth rod, no, there's nothing, 0. And the fifth rod is saying, yes, there's something, it's 2 units. But remember, they're all sending that to 1 bipolar cell. So now it's responding at, let's say, a level of 2, 4, 6. So it's not responding as quickly. Maybe the light doesn't look as bright, but we don't know, based on those rods, whether that's a dimmer light, whether that's 3 lights next to each other, whether that's 3 lights with darkness in between the first and the third and the fourth. We don't know. We lose that acuity. We lose that resolution because of that spatial summation, but it gives us that sensitivity to dim light. And I'm hoping that made sense. And actually, I'm going to come back, whether you're annoyed or you love it or you hate it, I'm going to come back to these circuits one more time after we talk about how neurons work, because I think it puts it together even more nicely and more clearly. And this is right now, the review so far, and it's going to include some things that we haven't quite gotten to, but the review so far. The photoreceptors, they're located on the retina. We have rods and we have cones. As we're going to get to some of the functional significance, cones are giving us our color vision and rods are giving us our black and white vision. What we have already done is the cones, we have 6 million per eye. The rods, we have 120 million per eye. The cones are mostly in the center or in the fovea, but remember they do lie in the periphery as well, at least a few and all around the periphery. The rods are only in the periphery. There are none in the center or the fovea. The cones are not sensitive to dim light. They are sensitive to detail. They give us our acute vision. And the rods are the reverse. They are sensitive to dim light because of the just vast amount of spatial summation of 120 to 1, but they're not sensitive to detail.